Welcome to this puzzle session. Here is the problem. Suppose we have n integers. N is some number, some natural number, at least 2, let's say. So suppose we have n integers. We want to show that some consecutive subsequence sums up to a number that is divisible by n. So let's see an example to better understand what is being asked. So we have n equals 5 and we have written some 5 numbers that come to mind immediately. So here we want to say that there is some consecutive chunk of numbers which sums up to a number that is divisible by 5. And a consecutive subsequence includes a single term. So this itself is a consecutive subsequence of length 1. So this doesn't work, this doesn't work, even this doesn't work. But if you just look at this, 4 plus 2 is 6, 6 plus 4 is 10, and this consecutive sum is indeed divisible by 5. N were 5 here, and therefore this, at least this sequence of 5 numbers confirms to this proposition. We want to prove this in full generality, meaning for any n. As usual, you're encouraged to pause the video before we look at what I'm going to discuss. And with that, let us continue. So we will define n other numbers. We have been given numbers a1 up to an. We will define n other numbers as follows. S1 is defined to be a1. S2 is defined to be a1 plus a2. S3 is defined to be a1 plus a2 plus a3, and so on. Sn is the sum of all of them. Okay. So each Si is itself a consecutive sum of a consecutive subsequence. S1 is the sum of the first one term, S2 is the sum of the first two terms, and so on. Therefore, if if Si is divisible by n for some I, then we are done. So assume that this is not the case. So in the adverse case, we may assume that no Si is divisible by n. Okay. So we have these numbers S1, S2, S3 to Sn. And what we are going to do is we are going to record the remainders of each of them when divided by n. So let's say R1 is the remainder that S1 leaves when you divide it by n. R2 is what we get for S2. R3 is what we get for S3, and so on up to Rn. So by this assumption, meaning the adverse case, we know that 1 is less than equal to Ri is less than equal to n minus 1 for all I. Why is that? Well, the remainder of any number when you divide it by n is going to be between, or is going to be one of the numbers 0, 1, 2 up to n minus 1. It's going to be one of these n numbers. If the number is not divisible by n, then the remainder is not going to be 0, and vice versa. And since we have assumed that none of these SIs are divisible by n, each of these remainders is strictly greater than 0. It is in this range. Okay. And now we have n numbers in this range, and therefore by the pigeonhole principle, since these are only n minus 1 possibilities for n numbers, by the pigeonhole principle or by common sense, some two distinct of these remainders must be equal. So we can write by the pigeonhole principle, there exist I and j in this range such that I is not equal to j and Ri is equal to Rj. Okay. So that's something that we should be comfortable with. And now, say without loss of generality that I is less than j. They are distinct integers, so one of them should be greater. So let's say I is less than j. And now we have Si, or rather let me write Sj minus Si is divisible by n. Why is that? Sj and Si both leave the same remainder when divided by n, and hence their difference is divisible by n. So this is in fact a very, very general fact. If you have two integers a and b and their difference is divisible by n, then they leave the same remainder when divided by n, and vice versa. If they leave the same remainder when divided by n, their difference is divisible by n. So this one should be able to prove for oneself if one likes. And now what is Sj minus Si? This is nothing but ai plus 1 plus ai plus 2 plus dot 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 aj. And this is of course a sum of a consecutive subsequence. So we have found a consecutive subsequence, meaning ai plus 1, ai plus 2, ai plus 3 up to aj, such that the corresponding sum is divisible by n, and that finishes the proof. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.